All right, let's just dive right into this explainer because today we are going to completely reshape how we think about computing architecture and Lisp design. We're not just looking at some system that tweaks how your code runs. No, we're looking at something that literally redefines the very geometry of memory and execution.
So I want you to hold on to one foundational question as we go through this material. What if computing memory wasn't just a flat plane, but a multidimensional coordinate space? Usually we think of memory linearly, right? Just a flat landscape of addresses. But what if we completely zoomed out? Imagine if every piece of data existed in this highly structured multidimensional space where its origin, its intent, and its structure were perfectly mathematically preserved. Pretty wild, right?
Okay, look at this quote. I know, it is an absolute mountain of dense terminology. Let me read it to you. A meta-ontology that fulfills definition of homoiconic, multi-stage metaprogramming meta-object protocol for metadata modeling, meta-knowledge, and meta-logic with a meta-circular meta-memory meta-compiler. A monad-transformer stack with a homoiconic metacon separation and quasi-group recovery, multilaxial multi-stage architecture. Whew. Yes, that sounds incredibly, ridiculously complex, but I promise you, don't panic. By the end of our time together, we are going to deconstruct this massive meta-word salad into an absolutely elegant spatial logic. It actually makes perfect sense once you see it. So here's our roadmap for today. First, the limits of traditional Lisp. Second, emergent axial architecture. Third, quasi-group recovery and meta-cons. Fourth, the pure monad stock. Fifth, multi-stage meta-compilers. And finally, we'll wrap up with the Omnicron coproduct.
All right, part one, the limits of traditional Lisp, or escaping the flatland. To really grasp why this new architecture is such a game changer, we have to start at the absolute root of the problem, which is how older systems handle data pairs. If you look at standard memory systems, they usually combine data using a plain XOR operation. And sure, that seems super efficient, but it has a fatal flaw. It's commutative and associative. Basically, if you combine a car and a CDR in traditional Lisp, they can irreversibly collapse into the exact same result. You lose their specific directionality. You literally can't tell which was which. But the solution here is the quasi-group cons. Instead of a simple XOR, it uses distinct, asymmetric, invertible transforms. This is huge, guys, because it preserves exact directionality. It guarantees perfect data recovery without having to add any bulky, memory-hogging tags to the system. Moving on to part two, emergent axial architecture, mapping coordinates. Now, what's really fascinating here is how we solve that whole flatland problem by introducing true dimensions to our code. In this architecture, which we call axial, a dimension isn't just a coordinate in some common numerical space. No, an axis here is a completely distinct coordinate family. It has its own unique laws and its own governing authority. You really have to visualize the data not as flat lines of code on a hard drive, but as something actively operating within a rich multi-axial coordinate system. Take a look at the 10 coordinate axes defining a conical runtime object here. A single object is no longer just some fixed host pointer or a flat tuple. Instead, it's this emergent relation mapped out across these 10 axes. We're talking about a scope coordinate, a structural coordinate, an origin coordinate, evaluation policy, temporal position, the whole shebang. Every single object knows exactly where it came from, exactly what capabilities it holds, and exactly what stage of compilation it's in. The object isn't just dumb data anymore. It's practically a living coordinate in space. Which brings us to part three, quasi-group recovery and metacons, solving the missing coordinates.
Let's dig a bit deeper and see how this builds into an absolutely incredible system of perfect data recovery. Remember that quasi-group cons we just talked about? Check out the sheer elegance of this math. Step 1, car combined with CDR equals the cons coordinate. Now, because this is built entirely on a quasi-group framework, the resolver log guarantees that if any one of these coordinates goes missing or gets corrupted, the system can perfectly reconstruct it from the other two. Look at step 2. Car dividing cons gets you CDR, and step 3, cons divided by CDR recovers car. It is beautifully bounded, completely reversible computation that seamlessly heals itself. No way data gets lost here. And to see just how deep this geometry goes, look at how polyadine to quasi-groups map these operations across the 4 vertices of a tetrahedral scope object. The system actually uses 16 possible 4-bit selection masks, which the source calls a cochord, to define exactly how these relationships are routed and resolved. It's not just linear math anymore. It is quite literally spatial selection defining what piece of data gets pulled from which vertex of the tetrahedron. It's like a giant self-assembling puzzle.
All right, part 4, the pure monad stack. Isolating meaning from effects. So the really absolutely crucial point here is understanding the architectural foundation that actually executes all this multidimensional tetrahedral math without just collapsing into total chaos. The entire reference architecture is built in pure typed Haskell. Now, pay attention to this part. While the monad transformer stock supplies controlled effects for the host runtime, it does not define the semantic meaning of the code. The core, meaning the parsing, the elaboration, the normalization, that all remains completely pure. Plus, by using existential packages, the system brilliantly hides those runtime-loaded axes behind heavily verified boundaries. So what does that mean for us? It means the effectful, messy, real-world runtime can invoke the pure core, but it can literally never corrupt the fundamental semantic truth of the data.
Moving to part 5, multi-stage meta compilers, passes as inspectable objects. Let's zoom out even further and look at how the code itself gets compiled in this totally pure multi-axial environment. You know how in traditional systems, compilation is basically a black box. Code goes in, an executable pops out, and you just trust the process. But here, we have a true meta compiler. Every single pass you see here, from the parser pass to macro expansion, all the way down to target emission, is represented as a distinct typed meta object. These aren't hidden, mysterious processes behind the scenes. They are tangible objects that you can inspect, interrogate, and as long as you stay within strict capability limits, you can even extend them. The compiler itself is quite literally made of the very dimensional coordinates it's trying to compile. How cool is that? And finally, part 6, the Omicron coproduct, system authorities and mediating maps. Let's take the ultimate zoom out and see how the entire runtime coordinates all this information securely. The source material goes to really great lengths to outline the corrected authority split for the Omicron protocol. It completely fixes older models where functions were just improperly lumped together. Notice how incredibly specific these rules are now. The tetragrammatron relation governor strictly adjudicates whether a relation closes mathematically, but it doesn't track where that data lives. No, that job belongs entirely to the Metatron incidence scribe, which records gauge incidence and carry. By separating relation closure from incidence tracking, this architecture makes sure that different layers can never grant themselves unauthorized mutation powers. It's airtight. So why does all of this meticulous separation and dimension building actually matter? Well, because in this system, independent knowledge sources contribute to a shared space through a coproduct mechanism. This makes cons the ultimate categorical blackboard compositor. It collects all these independent contributions perfectly, without ever erasing where they came from. One unique resolver map combines them into a shared plane, but mathematically guarantees that you can trace every single piece of data right back to its exact source and intent. Nothing is lost.
Which brings us to one final, really provocative thought to walk away with today. We have officially moved from a flat, destructive computing model to a rich, spatial, multi-axial architecture. An architecture where origin is perfectly preserved and missing coordinates can just mathematically regenerate themselves. Think about it. If our software can perfectly reconstruct its own intent and missing pieces without ever having to rely on destructive mutation, what limits actually remain on how software can heal itself in the future? It's an absolute paradigm shift, and I really encourage you to keep exploring the dimensions of this incredibly fascinating architecture.